So let's look at here, Doppler effect, okay. The first point, okay, the first point that we need to know is that, so we have two objects. The first object is the observer or listener, as you see here in this definition, okay, in this explanation. The first one is observer or listener. So there is an object that receives the waves coming from the source, okay, that's what we call observer. When do we call it observer? When do we call it listener? When it is sound waves, we call it listener, as you can understand from the meaning. When it is light waves, we call it observer. So if I use observer and listener, don't mind it, please. So both of them talking about the object that observes or receives the light or the sound waves coming, and then talk about the Doppler effect. And the second one is what we call is the object, what we call as the source of the waves, okay? So source of the waves, I just talked about the siren on a police car. So the one that produces the waves, okay? Where the waves are produced, okay? That's what we call as the source. For example, if there is a star moving away from the Earth and then radiates lights, and then you observe from the Earth by using a telescope. So in this case, is the star is the source of the light, okay? Source in this case, okay? So, and the next important point is the pitch or the frequency. We said pitch is a quantity and a property of waves that depends on the frequency, okay? That depends on the frequency, as you all know from grade 10 electromagnetic radiation, okay? We don't have to talk about this. You know what is frequency. I just want to start with the first two statements. The first statement says that as a wave source approaches, so which means that you are standing, for example, and then there is a police car coming close to you, approaching you, okay? And an observer encounters waves with higher frequency, okay? Which means that the pitch of the waves, sound waves, for example, in this case, the police car, okay, the siren from the police car. So you are going to have higher pitch and higher frequency. That's where we use how we are going to talk about the Doppler effect. And the second one is as the wave source moves away. So imagine that it comes in front of you, the police car, and then it started moving away from you. For example, chasing another car that is speeding up. And then what happens is that an observer encounters waves with a lower frequency. So which means that imagine that the police car is standing, not moving, and you are standing also, you are not moving, okay? If both of you not moving, what is produced, okay? The frequency of the sound waves produced in the police car siren is going to be what is heard by you. The time when the police car starts moving, okay? For example, it can come close to you, approaching you, moves towards you, okay? Or it can move away from you, moving away from you. In these two cases, the frequency produced by the police car, okay, the siren produced by the police car, the frequency will be same. But the frequency heard by you in the case when it approaches you will be higher than what is produced by the police car. And if it moves away from you, it will be lower than, okay, the frequency will be lower than what is produced by the police car. So this apparent change in the frequency due to the motion of the source or the receiver, there might be possibility, and then you are the one producing the, for example, source of the waves, and the listener can move. In that case also, there might be a change in the frequency, and this is what we call as a Doppler effect. And the greater the speed of the source, this is another important point that we are going to see later in the formula, you will easily understand that, okay, if the speed of the source is higher, okay, greater, and you will expect more Doppler effect. So which means that there will be a more change in the frequency, okay? There will be a more change in the frequency in different ways. And when we look at the sound waves, okay, first of all, we are going to talk about the effect of Doppler, the effect of Doppler effect on the sound waves. And I just want to talk about sound waves. If you remember from grade 10, electromagnetic radiation, and then before that we talked about longitudinal and the transverse waves. And the sound is a longitudinal pressure or wave. We talked about compression and rarefaction, if you remember. And we are going to talk about waves in the range of hearing, okay? We said that it's between 20 hertz and 20,000 or 20 kilohertz. Actually, if you remember when we searched on the internet that time in the class, I told you that we mostly can hear between 1,000 to 5,000 hertz. So it's very extreme, okay, extreme numbers that it's not easy for anybody to hear, but it's around 1,000 to 5,000 hertz, around that. If you search on the internet, you can easily see. And we can talk about the intensity levels, and that's what we measure, how we measure the intensity of sound waves in decibels for different sound waves. And then if it is like busy traffic or the vacuum cleaner, you know that vacuum cleaner, when you clean the house, wipe the, okay, the carpets, okay? So what you hear is that it's around 70 decibel. It's a noise, okay? For example, when you whisper, it's around 30, okay? When you talk about mosquito, for example, during the night, there is mosquito in the bedrooms, and then you can hear that the mosquito buzzing, and it's around 40. When you talk to somebody, it's around now, currently, it is around 50 decibel, okay? So if the decibel is higher intensity of sound waves, so what you hear is that, okay, it's going to damage your eardrums. And when we look at the Doppler effect, okay, there's another way of explaining Doppler effect. This is a good example. I just want to read it through and then show you on the diagram. So you can just focus on the diagram when I'm reading this. Imagine a bug jiggling, so which means that it jumps up and down. Imagine those bugs on the water. Sometimes you can see that they can stand on the water with big legs, okay? And then they are very small. And we talked about this also actually in grade 11, if you remember, under the topic is what we call a surface tension. We said that because of these animals, or we talk about the insects, okay, they know how to use the surface tension given by Allah Ta'ala. They know how to deal with the surface tension, and they can walk on the water, okay, because they know how to use the surface tension. And what happens is that this one, okay, is the bug, okay? So when it jumps up and down, that's what we call a bug is jiggling, okay? So it's going to create water waves in circular. It's what we call as makes concentric circles. And these are the waves. When you look at from up, okay, up position, and then you watch this bug, and bobbing up and down, jumps up and down, middle of a quiet puddle. And the crest of the wave, it makes are concentric circles because the wave speed is the same in all directions. As you can see, some of the waves are going to move up in the north direction according to diagram. Okay, I'm talking about according to diagram. And when we look at to the right-hand side and to down, up, they are going to have all the same speed, all the same wavelength. As you all know that, okay, the distance between these line and this line is what we call as the wavelength, okay? And distance between these and this one is what we call as a wavelength. So which means that, as you can see, the wavelength here and the wavelength on this direction, wavelength on this direction, wavelength between these 2 points is same. Everywhere the wavelength is same. So which means that if I am standing by B or observing from B, side B, I'm going to see that the waves coming with a wavelength, it is equal to the waves coming with a wavelength on the other side, okay? And then they have the same speed. Imagine that you have water waves, you have same wavelength and same speed. That's the point. Because the wave speed is the same in all directions, because this is the one creating and it does it in the same way. Imagine that, okay? It's not possible maybe in the nature, but assume that it's like that. If the bug bobs in the water at a constant frequency, okay? When it jumps up and down, it is in a certain amount of time. For example, it's in every 0.5 seconds. It jumps up and down. This guy knows how to watch the time, okay? It knows how to make it constant frequency. And the wavelength will be the same for all successive waves, okay? So that's going to be the distance between these two and distance between these two. and distance between these two and these two is going to be same. So which means that if you are standing by this side and this side as an observer, as you see here, you are the observer now, A or B, or this is the buck, this is the source of the sound waves, and you are going to see that same speed, same wavelength, same speed, same wavelength when you're standing at point A and B. Two people, for example. The wave frequency is the same as the buck's bobbing frequency. And in a case, what happens is that this buck started moving. It wasn't moving in this case. It was just bobbing up and down, jiggling, but up and down, okay? And bobbing up and down. And what happens? It started moving to the right-hand side. As you see here, it's also your right-hand side. So it started moving to the right-hand side, to the B. When it is still bobbing, okay, with the same frequency, and then it is moving to the right-hand side with a constant speed or velocity. And then what happens? As you see that there is a change in the circles. And if you look at the right-hand side, you are going to see that the distance between these two lines and these two lines is not as before. Can you see this? So the distance between these two lines and these two lines is not same anymore. And distance between these two lines and these two lines is not same anymore. As you see, when you move to the B, okay, so in front of the buck, what will happen is that those lines are going to come close to each other and the wavelength is going to be smaller. Lines coming together and the wavelength is going to be smaller. And if you look at the behind the buck, when it is moving to the right-hand side, you see that this distance and this distance, the line between these two distance is going to be, the distance between these two lines is going to be bigger. So which means that wavelength is going to increase. So the buck maintains the same bobbing frequency as before. Frequency, okay? Frequency where the waves created by the buck is same. Frequency heard, observed by B and is not same. In this case, okay, in this case, when it was not moving, the frequency created by the buck, frequency observed by B. Frequency created by the buck, frequency observed by A. Wavelength is same, speed is same. That is why. But in this case, so what happens is that the wavelength, okay, the frequency, wavelength is same actually, okay, they are related to each other, okay, they are related to each other. So we are going to discuss now that the relationship. So the frequency produced by buck is still same, it is moving, but the frequency observed by B and observed by A is not same. Why? Because the source or listener or observer is moving. In this case, the source is moving, the observers are not moving. And however, an observer at B would encounter a higher frequency. How do I know it will encounter a higher frequency if the buck is moving towards the observer? As you can see in this arrow, you can see that towards the observer, which means that the source producing the same frequency, but the frequency observed by B is not same, okay? And each wave crest has shorter distance, okay? So shorter distance, this is crest, as you all know from grade 10, okay? So what happens here is that, okay? So this one is a crest, this one is a crest. When you look at from up water waves, okay? You remember this story, okay? We discussed this. Okay, and then what happens is that, okay, so the wavelength in front of the buck is going to be smaller than original one when you compare with original one. So if the wavelength, if you remember this formula, speed of wave is equal to wavelength times frequency. We know this formula, and you just divide both sides by wavelength. Okay, if you divide by both sides by wavelength, what will happen? So we are going to have frequency is equal to speed of waves divided by wavelength. We said the speed of waves is same. The only difference, the change is the wavelength now. So in front of it, what happens to the wavelength? Smaller wavelength. If the wavelength is smaller and the speed is same, what will happen to the frequency? higher. So which means that in front of the bug, where the side B observer is, there's going to be higher frequency received. Okay? And if you look at behind the bug, I'm just going to close the video now, and then we will start again because we have a time limit, 40 minutes, sorry for that. And then we will carry on, inshallah, for the next half an hour. Okay? And each crest has to travel farther than the one ahead of it due to the bug's motion. So what happens is that behind the, at the back of the bug, behind the bug, so you see that wavelengths are increased. So if there's an increase in wavelength, the speed of the waves is same, and what we are expecting, frequency is lower. So which means that we are going to have higher wavelength in front of the bug and lower frequency according to the formula, higher, it is the same thing, by the way. Okay, I'll change it, inshallah. Can I just change this? This one is supposed to be higher. Sorry, my mistake. This one is supposed to be, so it is, if it is behind the, if it is behind the wavelength, behind the bug, sorry, and the wavelength is going to be higher, is that correct? Higher wavelength, lower frequency, and lower wavelength in front of it, there's going to be higher frequency. So which means that if you are the observer at B, what is produced here, the frequency, is when it comes to point B, it's going to be higher frequency because wavelength is going to be smaller and the speed of the waves are same. And if you are observing from here, what you are going to see is when the bug is moving away from you, when the source is moving away from you, source is moving away from the observer A, what will happen? You are going to have, longer wavelengths and then lower frequency, that is what we call as Doppler's effect, And where do we see this Doppler's effect, I'm just going to talk about, the sound, the Doppler effect causes the changing pitch of a siren. For example, when a fire truck approaches, the pitch sound higher than normal. So which means that what happens in this case, if you look at here, similar to the bug, so there are sound waves. Now this one is moving, and in front of the moving source, what happens? The wavelength becomes smaller. If the wavelength is smaller, as you see here, wavelength is smaller, speed is same, and the frequency is going to be higher. So which means that if the fire truck is approaching you, moving towards you, what will happen is that you are going to hear higher frequency. And after a while, what happens? It comes in front of you, and then as you see in the diagram, it's waving you, the firemen, they are waving you, and they say hello, and then when it is moving away from you, now you are in the case of A, you are like A, this is the fire truck, and behind the fire truck, what will happen? There will be longer wavelength, and if the wavelength is longer, speed is same, there is going to be lower frequency, and the frequency is going to be lower. And when a fire truck approaches, the pitch sound higher than the normal because the sound waves crest arrive more frequently, wavelength is smaller, frequency is higher. When the fire truck passes and moves away, you hear a drop in the pitch. Pitch is a quantity, it's a quantity, physical property of sound waves. It depends on frequency because the wave crests are arriving less frequently. So the crests are moving away. You know the distance between two crests is what we call as the wavelength. So the wavelength becomes bigger, frequency becomes smaller. The change in loudness is not Doppler effect. It is the shift in the frequency, So let's talk about this also. Where do we use this Doppler effect? I'm going to talk about this too. We have 4 minutes. I can just talk about this too quickly, and then we can just go off and go on because we have 40 minutes limited time, and then we can just join again. Sorry for that. And then inshallah, we will carry on with the class until 3 o'clock. So Doppler effect, where do we use this? Where do we use this Doppler effect? Let's look at here. Police use Doppler effect of radar. You know that when you buy a new car and you want to check that what is the highest speed on this car, okay? So, and after a while, what happens is that, and then police use Doppler effect of radar waves to measure the speed of cars on the highway, and they got you, and then they are looking for somebody's driving over the speed limit, and the radar waves are electromagnetic waves. Police bounce them off the moving cars. So they send waves, okay? They send waves, this is source, okay? The waves going to the cars, and the waves reflected from the cars. When they are reflected from the car, because of the motion of the car, there is change in the frequency of the waves reflected. And radar waves are electromagnetic waves. Police bounce them off moving cars. A computer built in the radar system compares the frequency of radar with frequency of the reflected waves to find the speed of the car, okay? And there is another example. I just want to move to the next point, okay? Inshallah. Okay. And where do we use it? It's a medical purpose, medical use. That's what we call as Doppler flow meters. And the ultrasonic ultrasound are sound waves with frequency greater than 20,000 hertz. It's just about the frequency that we can hear, okay? The upper limit of human hearing. These waves can be used in medicine to determine the direction of blood flow. And the sound, the device called a Doppler flow meter sends out sound waves. The sound waves can travel through the skin tissue and will be reflected by moving objects in the body, like blood. The reflected waves return to the flow meter where its frequency, received frequency, is compared to the transmitted frequency. So you send the waves with a frequency, and after reflected from red blood cell, for example, in this example, I found it from internet, okay? There are lots of examples you can find. And then what happens is that, so there is another frequency reflected because of the motion of the content of the blood, and the reflected waves return to the flow meter where its frequency compared to the transmitted frequency, the one that you sent. And because of the Doppler effect, the blood that is moving towards the flow meter will change the sound to a higher frequency, and the blood that is moving away from the flow meter will cause a lower frequency. And then you can understand that, is there a blood clot, okay? Is there any problem with your blood vessels, etc.? Or there is something else, that's what we call, they also use ultrasound to be able to understand the blood flow and the direction in the circulation system of unborn babies, okay? And identify the areas where there is no blood flow or restricted flow, there is problem, and if you want to check, okay? That's another example. So which means that before we close now, okay, less than 1 minute, we use for the speed radar for the police, and we also use it for something called Doppler flow meter, and that's what I'm going to discuss, calculation part. So can I just stop sharing, okay? I will just, okay, close this and then stop this, and then you can join again. I'll just send you the new one, okay, meeting, and then we will carry on for the next 20 minutes, inshallah. I'll just end the meeting and then you can join again.